Welcome all to today's Passive House Alberta Building Better in Alberta webinar series, sponsored by the Alberta Eco Trust. My name is Frank Crawford, and I am the Education Committee Lead for Passive House Alberta. And today we will hear from Steve Cox, who is the Building Envelope Technician and an Energy Consultant with Qualistat Building Performance Consultants in Calgary. And we'll be hearing all about the need and the importance of a mid-construction blower door test and what it is. First, I would like to thank the Alberta Eco Trust for their ongoing support. It is very helpful in allowing Passive House Alberta to continue our work. And as always, you can place your questions in the chat box and I will ask them at the end, or you can unmute and ask them yourself at the end. And with that, please now take it away, Steve.
Thanks, Frank. So I was approached by Passive Alberta to talk about mid-construction blower door testing for you on this presentation. It's something that we do a lot of at Qualistat Building Performance Consultants and the VT group of companies. We're out doing them multiple times a week. So we thought this would be a good subject to present on. That's why we're talking to it now. So a little bit of an agenda here, just to go over all the stuff I've got for you. If you're playing the home game, we've got 37 slides to get through. So you need to know how we're pacing. That's what we got today. So I'm going to introduce myself, give you a little bit of my experience, define what blower door testing is. I know that this presentation lives online after a period of time, so I figured that would be worthwhile to do. Define what it is for those of us who may not know. Talk about blower door testing results, specifically metrics. We know about ACH, for example, in the Passive House community. There are other ones. So we're going to talk about that. We're going to talk about how they get calculated as well. Going to talk about the airtightness code references. So that's in the current 2023 National Building Code Alberta edition, as well as the proposed 2025 National Building Code. It should be adopted in Alberta in 2027 if everything runs on schedule there. We're going to talk about sequencing and coordination of blower doors, what we're looking for, when we're looking for it, why you would choose one stage over another. I have a couple of case studies for you with pre and post and different airtightness strategies as well. And then I also wrangled in some testimonials for you from builders in our roster of builders. And these are builders, just to give you an idea, combined, these builders are responsible for over 1,000 houses in Calgary and Alberta every year. So it's quite a large sample of people who are taking this on as a part of their build. So words from the builders themselves is what I have for you at the end there that I will direct to you, their written comments. So first off, I'm Steve. I've been a Passive House consultant since 2017. As a founding member of Passive House Alberta and a previous board chair. I still sit on the board of Passive House Alberta. Enercan, a registered energy advisor since 2018. I've been in the construction industry in one capacity or another since about 2010. Level 1 thermographer, so that's infrared imaging. That's typically how we do our blower door testing, is with infrared imaging to try and locate air leakages, but we'll get to that in a little bit. IDP facilitator, so that's the integrated design process. That's a program pioneered by Casey to try and get the build projects, everyone in the build project in a room before the build starts to make sure everyone's on the right page, reduce work orders, that kind of thing. So I'm facilitated for that. CHBA Net Zero Energy Advisor and also a moisture control technician. I've been that for about 6 years now. So that's how I came to this position here in front of you today. So we're going to talk about blower door testing. This is a blower door system set up in a pre-drywall test that I did a couple weeks ago. So this, what you see here, we've got the fan, right? We have different openings in the fan to control how much air can flow through the fan. I've got a manometer up here. If you forget what it's called, the Muppets have a song about it. But what it does is it tells me the pressure differences, right, between inside the house and outside the house. It also tells me the pressure differences in the fan. I can do rough calculations through the manometer as well. It gives me airflow. It can give me area leakage per area, which we'll get to in a little bit. So I wanted to talk to you about 4 basic strategies for air tightness testing. The first one is a positive pressure test. In that instance, what we're doing is we're going to induce more pressure into the house, kind of blowing it up as it were. Then there's the negative pressure test where we're sucking it in. That's what this particular setup is for. So the air is flowing out of this fan in this configuration, creating a negative pressure related to outside. Then I have the EnerGuide compliant testing we're going to touch on, which is a modified CGSB test. Basically, the most important part about that is that it's a multi-stage, multi-point test is what it's called. And then I'm also going to talk on the EN 13829 air tightness standard. That is the passive house compliance standard. So we're going to talk about the differences between some of these tests, just so anyone who's curious wants to know why we would do a certain test over another. That's what we're going to talk about here. So the first one is a positive pressure test. So in this case, what we're doing is if we're running a fan, we're bringing air into the building, right? We're blowing it up. We're pushing the poly and the air barrier outwards. An advantage to this is if we're doing a mid-construction blower door test, typically the air barrier in a construction house in Calgary, the air barrier is our poly layer, which is that plastic film. If we do a positive pressure test like this, what we're doing is we're pushing that poly up and against the walls. So there's no risk of me tearing it down off of the studs and attic trusses. Okay, that has happened. If there's a wind or the fan goes crazy, sometimes that happens. So when I'm doing a pre-drywall mid-construction blower door test, I'm going to run it at a positive pressure when I want to get a reliable number. When we're doing testing, typically we go to 50 pascals of pressure. So if I run the fan to a positive 50 pascal pressure inside the house, what I'm doing is I'm pushing that poly out. I'm pushing it against the walls. I'm not pulling it away from the walls. So I'm going to get a more accurate number, and there's less risk that I'm going to damage the building by doing it this way at a mid-construction. When I'm doing a negative pressure test, this is typically what I do to do investigations. So the advantage with doing a negative pressure test is that when you're walking around, you can feel the air coming in at you, right? Or when I'm using my infrared camera, what I can do is I can see the air leaking in through the assemblies because it's blowing in towards me. When I'm doing all this mid-construction tests, I'm always inside the house. So that's the negative pressure test. As you can see, we're sucking in the walls and the ceiling. So when I do this testing in mid-construction when there's no drywall on, I'm not going to the full 50 pascals, right? That's going to increase my risk of pulling poly down either off of a wall or typically off of an attic space, and then my test is ruined. And now the insulator isn't happy with me, and I don't get hired again for that job, right? So there's a whole bunch of problems there. So what I'll do is typically go to half, maybe 20 pascals, maybe 25 pascals if the conditions allow, and then I can walk around and I can look for air ingress through these assembly details. So that's the negative pressure testing. EnerGuide testing, what that is typically that's done at on a house. This is going to be with the CGSB. We can do it either a positive or a negative test. The vast majority of the time, we try to do negative pressure testing when we're doing EnerGuide tests, because what happens is we have the drywall on typically when we're coming to an EnerGuide house, right? If you look around your house right now, you shouldn't see a whole lot of poly. You should see a whole lot of drywall and paint. So the drywall is on to compress that poly and keep that air barrier in place. So it can take a lot more pressure negatively. And then if we also run the CGSB test negatively, what we're doing is we're pulling dampers closed, right? So like around the range hood exhaust, at the bathroom exhaust, there are dampers inside those fans. And when we do a negative pressure test, we're pulling those dampers closed. It's going to give us a better number. Okay. With the Denmark, the passive house standard, the standard used by the International Passive House Institute, that test requires both positive and negative pressure testing. Okay, so we can't just do negative because it skews the numbers. And Passive House understands this, and that's why they chose this standard for their air tightness. So this is a graph I did on a project that required Passive House compliant testing. We're going to get to the actual project in a little bit. It was not a Passive House project, but one of the requirements for this builder was to deliver to their client, which was the federal government, a project that was that met at least passive house standard for air leakage, which is 0.6 air changes per hour. Okay. So on this one, as you can see, we have our negative pressure testing relative to outside. So we have the fans blowing out air from the building in this instance, and then we're blowing air into the buildings in this instance. So we have to flip the fan physically around and blow air into the building. And you'll also notice this is the induced pressure here on the left on our y-axis. And even though the ACH number comes to us at a pressure differential of 50 pascals, which is right here in the middle, we're coming down to negative 80 pascals and positive almost 90 pascals on this particular test to do this testing because of how far apart the points need to be, how long the points need to be measured for. That's where this testing comes from. So even though the number's at a 50 Pascal, we have to go much, much higher in the EN standard, the Denmark standard. And yeah, so this is data that's collected on a software called Fantastic, comes from a company called Retrotech, who actually makes the blower door systems. It's a really good piece of software. I like using it whenever I have something complicated. I'm going up next week to Jasper, and we have to determine how much air leakage is in a single unit of an apartment complex. So we're going to use the Fantastic to control the fans all around that unit to reduce air leakage between the units so we can get the true air leakage in just the unit itself as opposed to air leakage through the party walls and through the floors. So I'll be using Fantastic for that as well. Talking a little bit about blower door test results. So the typical one that we know of in North America is the air changes per hour. Okay, ACH at 50 pascals. That's what this number is here. As I go through here, this is one of our standard sheets that we do for reporting through Qualistat. So this was a site that I went to earlier this year. So it's got the house, it's going to have the address and the client. I didn't get that approved, so I didn't put that in here for you. It's got some comments on how the building was constructed at the time of the site visit. And then it has the metrics, right? The results of everything that we got from this testing. So air leakages per hour, that's this top number here. So in this case, it was a 2.35 in this particular instance, which is, it's fine for a post drywall, in this instance, mid-construction blower door test. We also have a metric called equivalent leakage area. Okay, this is done in square inches or in square centimeters at a pressure of 10 pascals. This one is not well reflected. No, it is. It's reflected right here in the bottom here. So in this one, it was 196 square inches in this particular instance. Normalized leakage area is leakage area per square meter or per 100 square feet. So this one is not reported in our report. This is not one that is asked for typically. It is something we can calculate using this, and I'll show you that in a minute. And then normalized leakage rate as well. This is the NLR. So NLR is this one here, a 1.09. Okay, so we'll talk about what those things mean in just a second here and what we can use for code compliance as well. So air changes per hour, ACH at 50 pascals. This is pretty common. This is the one that we understand. So we take the flow rate through the building at a set pressure, reported at 50 pascals pressure, the air movement rate through the fan measured over an hour compared to the volume of the house. And it's really good for larger buildings. Okay, so the math works better the bigger the volume is in relation to the wall surface area as a portion of air leakage. So here's the ACH that we have, right? This is our flow rate in CFM. So that's in cubic feet per minute. So we have to multiply that by 60 to get our cubic feet per hour and then put that over the volume of the house. And that gives us our ACH. Equivalent leakage area. Okay, that's this one here as again. So it's measured of an equivalent. This is a little bit complicated. So let me see if I get this right. So the equivalent leakage area is the idea that if we add up all of the holes that air is leaking through, the resistance to airflow of that one hole is equivalent to the overall air leakage. So what that means is it's the resistance of movement around the perimeter of a hole of that diameter, rather than adding together every little leak and making a hole, and that's how much leakage area we have in total. It's a really complicated thing to understand. It's also a difficult metric to get consistent and comparable results on. I've got one later on here that's going to show you what I mean by that. But there's been a number of projects where we go to when we do the pre-renovation, the pre-construction, and we get a EQLA of X, whatever it is, but an ACH of, let's call it like this one, 2.35. We go in and do the final later. The air leakage, the ACH has come down. Maybe it's a 1.5 now. So they've made an improvement, but the EQLA is still at that same level, or sometimes it's even higher. So it's a really difficult metric. It's really unreliable in terms of comparing what's happened to the building. And yeah, so that's a word of caution against using that as a reliable metric, is what that comment is. Normalized leakage area. So for this one, we're using the EQLA number, so our 196 square inches on this one, and then we're going to put that over our total envelope area. In this case, just based on how the reports go, the one software spits out a square inches number, the other software spits out a square meters number. So this one doesn't quite add up terribly well, because it should be square centimeters into square meters, so consistent units in that. But that is how this number is calculated. It's the average leakage per portion of the building envelope. This is one of the metrics that, as we get into step code, tier code, this is one that can be used. The office here was just out in BC doing testing on a large building, and they had to meet a certain normalized leakage area rate before they could turn the building over. And when we're calculating the building envelope too, we should include that this number includes all 6 sides of the building, right? So all 4 walls, the attic, as well as the slab, whatever that slab is, right? So the envelope area, even though we have a portion that's underground, it has really low leakage area because it's underground, that does still count as an above grade wall area. So that benefits us when we have, like in Alberta, when we build basements, that's beneficial to our calculation here, because it's a really airtight assembly in terms of normalized leakage area. Finally, we have a normalized leakage rate. Okay, so this is our NLR number here that I showed you, the 1.09 on this one. So it's liters per second per square meter of envelope area, or CFM per square foot of envelope area. Here at our office, what we're doing is we're defaulting to the liters per second per square meter, because that's how it's laid out in the code. And as you can well imagine, liters per second per square meter is going to give us a lot different number for the same leakage rate compared to a cubic feet per square foot, right? The ratio there is not comparable at all. So we're on our reports, we're going with liters per second per square meter to try and embrace this as a possible air leakage metric to use on buildings going forward. The flow rate is measured through the fan at 50 pascals pressure differential over the envelope surface area. Okay, so on this one, I have 805 liters per second is what I measured when I was at 50 pascals on this one. And then again, that's our envelope area is 736 square meters. Again, it's all 6 sides of the building. And then as we get to smaller buildings, right, townhouses, small houses, if we're getting to stuff like that, then this metric works a lot better to get compliance versus an ACH, right? If we take a small building and we put a little bit of flow through it, because we're putting that small flow over a small volume, that ACH can get out of hand quickly. Because if we're using the flow rate through the envelope surface area, the math is more in our favor. Okay. So let's talk a little bit about code compliance metrics as laid out. So this one is the 2023 Alberta edition of the National Building Code. It's been in force for a year now. Performance modeling does not require blower door testing as part of the 936 code compliance for energy modeling at this time in this code iteration. So before I get into that, what we have here is these tables here do not change between this code and next code. These are the same tables. What they show us is the air tightness requirements for single zones and attached zones using the guarded method. Okay, so I'll tell you what that means in a second. But just to look at some familiar numbers here, so we're looking at ACH first. So this level 1 is a 2.5 ACH, which is laid out in the code as the expected maximum air leakage that you don't have to prove, but the expected maximum air leakage of a building that's new build in Alberta in since May 2025. Okay, that's what this item says here. Then if you move up in air tightness, now we're down to 2 air changes per hour, right? We've reached another air tightness level. And you can see there's corresponding NLRs, liters per second per square meter, over here that correspond with the same level of air tightness, right? So on that house I gave you, we had a 2.35 ACH. So that's going to put us at the air leakage level 1. However, it was a 1.09 NLR. So it would not meet the level 1 compliance for NLR. Same building, it just depends on which metric we're using. Okay, so it passes with ACH, no problem. Not that this has to pass, but in this instance it does, just for this example. Okay, so single zones and attached units determined using the guarded method. A guarded method is, as I described earlier, what I'm going to do in Jasper next week. So if we have a townhouse, a row house, we have 3 houses in a row, all attached to each other. I want to know what the middle air leakage is, but I only want to know where it's leaking compared to outside, not compared to its neighbors. So what I'm going to do is I'm going to set up a fan in unit 1. I'm going to set up a fan in unit 2. I'm going to set up a fan in unit 3. And I'm going to run them all at the same pressures at the same time. So I'm going to go 15, 20, 25, 30, 35, 40, 45, 50, right? All the way up. And what happens is then I'm taking out that party wall, that demising wall between the units as a pressure, as a point where air can leak, because the fans are going up at the same pressure. So they're depressurizing at the same rate. So now the only leakage I'm getting through that middle fan is air that's coming from outside. Okay, so that's a guarded test. So we have 1 air change per hour in a guarded test situation, and then we have another air tightness target for unguarded. So in EnerGuide, they don't let us do the guarded test. So if I want to do air leakage testing on just the middle unit and they want an EnerGuide label for it, then I have to only do that middle unit. So as a result of the leakage through the party walls, they've given us a little boost to the ACH and a little boost to the NLA and a little boost to the NLR, right? So 3 air changes per hour is what they've given us for zone 1 in this instance, compared to the 2.5. They've given us 1.17 NLR compared to the 0.89. So they've given us a little boost to accommodate for the air leakage through those adjoining walls, which are not cold air like it would be through the front and back of the house. Okay, hope that makes sense. There is a guideline for tier code in the existing Alberta Building Code 2023. It is this table here. Currently, the only enforced tier is tier 1. So you just have to prove that you're better than your house uses less energy than a reference house. It is better than a reference house. That's all we have to prove. Okay. These other tiers, there's no current plan that we know as energy advisors, as envelope consultants. There's no current plan to use tiers 2 through 4 in the current building code. Okay, that's all I wanted to say there. And then also, as tier code becomes more common, this is again the 2023 code, they've laid out performance tiers. You can get energy conservation points. If you wanted to achieve tier 2, that would be 10 energy conservation points. If you're curious about that, that's another discussion we can have. I'm happy to have that discussion with you separately. I don't have time to go through that now with you. Okay, so now jumping into the next iteration of the building code, which was released in December nationally. So the goal of the building code is that it's released and then the provinces have 18 months to adopt it to their own jurisdiction. So that would put us about May of 2027. Not a whole lot changes in this code. We do still have a performance path. It's better defined in this performance path, as I'll show you here. So this remains the same. This table remains the same. The definition of each tier, tiers 1 through 5, remains the same in terms of energy consumption, right? So right here, tier one, we still have to be better than the target house. We still have to show improvement. That's the same, has not changed. Um, going forward, there is also a performance tier. There's trade-offs and points available. So now they've defined how many points it's going to take you to get through the performance tier using various choices you can make inside the assembly, inside the building construction. So if you need to get to tier two, it's still 10 points. Now tier three is 20, tier four is 40, tier five is 75. Okay. What we're going to do is this table is also the same. This is the air leakage table. Okay, it's the same as it was in 2023 as it is in the 2025/2020 code. Will be the same. So what does that mean? What that means here is, so we're looking at so this is a points table now. So when we're looking at the performance of air leakage in particular, when we're talking about housing, what kind of points does air leakage account for? This is something Frank wanted me to mention on how to achieve tier code by doing better air tightness. Okay, so I brought that table forward as well. So we're going to use that same single zones and attached using the guarded method table that we discussed earlier. So pick your zone, whatever zone you like, right? So we have zone 6, zone 7A is the light pink, zone 7B is the darker pink, and then zone 8 is the purple. So pick whatever zone you like. They're all labeled here as well. Okay. Alberta does not have any zone 4 or zone 5, so that's why I crossed that out for you. So if we take our building, our sample building, that's at 2.5 air changes per hour, we get 0 points at any climate zone for 2.5 air changes per hour. Okay. If we bump that to a 2 air changes per hour now, we bring it over to this side of the table, right? Now we have 3.5 points if we're down in Medicine Hat, Lethbridge. We're at 3.8 points if we're in the bulk of the province there, Calgary, Edmonton, Cold Lake. We get 4.3 points if we're Fort Mac. And then if we're with Buffalo area, 4.8 points, right? So there is a greater incentive. The colder you are, there's a greater incentive to air tightness. You get more points for it. So if we extrapolate here, if we take the tier 3 air tightness, so we bring that our 2.5 down to a 1.5 building. Now, if we're up in Wood Buffalo there, we get 9.7 points. That's almost tier 2, right? Just bringing down the air leakage has bumped us to tier 2 if we're doing the points performance method. There are other methods of compliance, but just humor me that this is the only one for right now. If we bring it down to a 1 air change per hour, so that's our net zero standard, right? If we're chasing net zero, that's going to be our minimum air tightness there. We have to be 1.0 or better. Okay. And then anywhere in the province, if we achieve that tier 4, we get our 10 points, right? So just getting to 1 ACH or 0.35 NLR is going to get us to our 10 points for tier 2. Okay. In any instance, getting down to 0.6, the passive house standard does not get us above tier 2. Okay. In any instance, it doesn't get us above tier 2. If you get a attached product that you can do in a non-guarded method, then in northern parts of the province, now we're into tier 3, right? If we get to the 0.6 ACH. So that's kind of why it's important to know where the air leakage are, what the air leakage rate is, that kind of thing there. So timing of the testing. Typically, most of the testing we do is at pre-drywall stage. What does that mean? That means that the house is wrapped on the outside. It's got the Tyvek layer on the outside. We have we have the interior is insulated. The poly layer, right? The air barrier. Typically, we're doing a poly layer on the inside. On the inside there, that's in place. It's been stapled and it's attached. So this allows for precise pinpointing of air leakages. There is a risk of damaging poly-based air barrier layers because again, we're doing that negative testing. But it also allows you to repair them easily, right? So in this instance here, what we've got is air leakage around the frame of the window. Okay, we've got air leakage at the frame. They didn't put any insulation. There's no air barrier there. Okay, so it's easy to identify that and say, I know exactly where this problem is, right around the window. In this one, something else that we do is we take a look visually at the connections, right? So this detail is going to fail in the future because it is just a tuck tape. It's not a rated airtight tape. That kind of tape needs to be compressed to be effective. Just gonna check the time here. And so that air barrier needs to be compressed to be effective. That's going to let go in that particular instance. And then this is spray foam right here. So there's an issue with the spray foam. It's not continuous around this wood block area. It blows through. So when we had the house under negative pressure, we could feel the air blowing at us when we had this opened up because it was pre-drywall, right? This would be a hard leakage to find otherwise. Some of the tests we do are post drywall. So that image I showed you already, the summary sheet was from a post drywall. So when I went into that house, I was able to do a full negative pressure testing investigation. So I'm able to do the full numbers as if it is a final, pull that house down to -50. It's hard to pinpoint precise air leakages, as you can imagine. So in this one, I found an air leakage on the backside of the drywall right here in the middle of the house, right? So what does that tell me? That's really hard for me to tell. So I made a note of it. I'm going to show the builder. I'm going to say, Mr. Builder, this is what's wrong with your house. I don't know what's leaking here, but there's air leakage here. You're going to have to investigate that. And by the way, I'm taking my fan away from me, right? I'm taking my fan with me when I leave the house. So it's a more costly investigation if someone wants to solve the problem because they need to remove the drywall to access the air barrier. Like in this one here, there's air leakage that we discovered at the window frame to window jamb connection. And then this one, again, is in that pre-drywall house. The air leakage is coming under the bottom plate here. So there's not much they can do at this stage of construction to address that. So I mentioned earlier, something else that we do is we do a visual review. This is something that we do before we walk a site, while we're walking a site, before we blow it up, do an airtightness test. That's my language, blow it up. We do a visual review to make sure everything's going to work, right? All the windows are in, the doors are closed, the poly's all there. There's not a part that's missing. All that's going to impact how we, all that's going to impact the results of the blower door test and how effective it is. So at this stage, what we do is I'm looking at the bottom plate specifically of this wall. When we install drywall, it doesn't come all the way down to the floor. It sits up about 3/4 of an inch. So what I'm going to recommend on this one is that the compressive material, there's a bead of sealant where the compressive material sits, right? So the drywall needs to compress this bead of sealant for it to become effective. So there's going to be an issue here, for example. There, that's precisely where I wanted it. It's almost like I thought of this. So another instance that I'm going to flag on these walks is something like this here. So when the drywallers come through, they're going to drywall this ceiling, right? They're not going to come in and drywall this. This is going to be an air leakage because this material is not compressed. Currently, it is thick enough, but eventually this acoustical sealant will lose its tack. It won't be it won't seal the poly to the framing anymore. So we need to have a structural compression in place around this detail here to make sure that that air barrier stays in place where we want it to stay for the duration of the building. Something else we look at is we assess penetrations through the airtight layer. Okay, like this one here. So this one, they didn't even bother to try and tape this, right? So in a dry-walled blower door test, this is going to be a difficult leak to trace because we did this at pre-board. This is not a difficult leak to trace. We know exactly what's going on here. We can also review the window installation strategies. Okay, so I have done numerous talks on the relative, the standard CSA A440.4 for how to install windows and doors in Alberta as defined in the code. So this allows us the opportunity to evaluate this as well if we come into pre-drywall stage. This one is obviously not ready for pre-drywall. There's no poly here. There's no insulation around the window jamb at the rough opening connection either. A little bit about non-poly compliant air and vapor barriers. Okay, so this one is a good passive house one. Passive house likes to use the OSB, the vapor retarded uh, characteristics of the OSB, and tape it with an airtight tape around the joints. So that's what this one is. This is not a passive house. This is a garage structure in a multi-townhouse that we recommended they go through and do this. It just made more sense for how they wanted to do it. So they're going to install the insulation on the outbound side of this OSB here, and that's going to be our air and vapor barrier in that instance. So that's a really fun thing you can do when you understand how different components and different materials, their different characteristics. So you can break stuff up a little bit more and use different materials when you don't just think the only way through is poly. This one is a closed cell spray foam. Okay. The closed cell spray foam is an air and vapor barrier at about 2 inches thickness. So this one we did a pre-drywall blower door test. You can see the little red laser here. There was an air leakage at this connection. There was a steel to steel connection in this wall that wasn't treated with an air barrier. So when we did the negative pressure testing, we're able to go through and find those leakages with the thermal camera because it was warmer inside than it was outside. So those signatures show up quite well on the thermal camera in that instance. Really, a pre-drywall blower door test is highly recommended in my mind anywhere we have a spray foam assembly, especially if there's an unvented attic. So an unvented attic, I mean, if there's a flat roof or a cathedral ceiling where the spray foam is the insulation and the air barrier all in one. If we have a failure with that, then then the condensation can get in there and we have a big problem. So especially where there's an unvented attic that's treated with spray foam, but every building that has spray foam, in my opinion, should be very least treated with a blower door test to find problems, let alone to find the ACH and the NLR, just to find the problems so that it doesn't cause warranty work later on for the builder or the homeowner. This one here is a large project, an apartment building up in Edmonton, Veterans House. So what we're using here, this was the one I showed you the blower door data for, the passive house standard blower door data. I showed you that off the top there. This is the interior of that space at pre-drywall. So as you can see, what they've done here is this is a smart vapor barrier. This is membrane from Certainteed. That's a vapor open material. So what that means is if moisture accumulates inside this wall cavity, the membrane has the ability to become more vapor permeable to allow that moisture to breathe out into the space if needed. So that's what they've done here. This is a redundant air barrier layer. They've treated this interior as if it's the air barrier layer. They've compressed it everywhere because I have to do negative and positive pressure testing. This was a really good test. The primary air barrier layer on this one is the exterior. What they've done is a peel and stick material on this one, a 3M vapor permeable material on this one. So it's an air barrier and a vapor permeable membrane. So you can see it's a 3-story apartment building that they were doing this one on. Here's the renderings of it. So it needed to attain the Passive House International standard for air tightness. So I went out there and I did the compliant EN 13829 Denmark testing on that one. It was a really fun test. I brought up 4 fans. I needed only 1. That's how tight it was. So as you can see here, this is the output of that testing, of that compliance testing, and they got a 0.13 air tightness. So Passive House standard is 0.6. This is 0.13, an outstanding result for for a builder who hadn't done air tightness testing before. They expressed throughout the process a number of times how anxious they were. So we talked them through it. We got them to this stage, and that's a fantastic result for a pre-drywall test in this building. Gives them lots of room to work with for issues later on. Okay, so now into some case studies here. So I wanted to draw your attention to this one in particular. So this is a house in Calgary, in the southwest of Calgary there. This is our pre-drywall sample on the left. So we have an ACH of 3.78. It's okay. It's not a great pre-drywall number. Maybe there was a temp door or something that wasn't well sealed. Actually here, yeah. So there's a temp door that was fully not sealed, and there was windows open for electrical. So sometimes that's what happens. The power supply is hooked up to the panel in the basement, and then the electricians haven't electrified any circuits yet. So there's wires that run through the house, through the windows, to allow the guys outside power to do their job. So this one had a 3.78 ACH, a 1.34 NLR. This was a positive pressure test. Okay, so what we're doing is we're pressurizing the building rather than depressurizing the building. We have a flow rate of about 1,000 liters per second, so quite leaky. And then I also want to draw your attention to this here, a equivalent leakage area of 337 square inches. It was the equivalent leakage area on this one. Then I came back at final because that's what we're doing with this client. We're coming back at final. They want us to come out at mid and at final and do some testing at final. So this one, they had a significant improvement on the air tightness, right? They dropped it 3 air changes per hour. Closing a window will do that. It's amazing what closing a window will do. That also dropped the NLR quite a bit. And then that was a depressurization test as well. So we're pulling any dampers closed. But interestingly, the ELA remained the same at 3.37 square inches. Again, that's a software thing that comes from, in this case, Hot 2000 is the software we were using for these calculations. So this is another one in the northwest of Calgary here. So pre-drywall, they blew a 4.5. There's nothing too outrageous about it. We did this one a couple of times. They weren't too happy with the numbers. So we did this one a couple of times at pre-board. This was the second time we did it, so it came down to 4.5. 2.26 NLR. And again, this is a positive pressure test. And then this one here, the ELA is at 414 square inches. So quite a big hole is what we've found that to be. And then we came back at pre-occupancy. So this was done up as a show home. So before occupancy, it was at lived-in conditions. All the traps were full of water. All the finishes were in place. So that dropped down to a 1.09. ACH. Their target, they wanted to know how much further they needed to get to the net zero standard. So they're pretty close to net zero standard there at 1 ACH. So they're 1.09. They're close. A little bit of work. The windows actually on this one, some of the sealed units on the windows were leaking on this one for some reason. So they would have to get the window manufacturer out to look at that. The NLR reduced on this one quite a bit as well to 0.5. And then the ELA also dropped to 74 square inches. So that's a significant improvement in terms of the performance of this building. Okay, I'm into the testimonials portion here now. So in my ask for this, Frank it was encouraging in saying that he wanted to know what kind of builders were doing pre-drywall testing. So these are all, I won't go into all the testing we do for all of these clients that I'm about to tell you. I do have their permission to share these comments with you. These are coming straight from them. There are different sizes of builders that are presented here, and probably based on the text that they've provided for me, you can probably guess which builders are larger and are more accustomed to building reports justifying things. But anyway, so this is Ben from Mattamy Homes. He notes that their story with labeling and blower door testing goes back to August 2022, when Mattamy Homes made the decision to label every home, and that gave them a strong data set to understand which products and details were performing well and which needed improvement. That allowed them to shift their insight into focus on the worst performing areas. Ben goes on to note about how drywall and finishes can hide air leakage points, and that helps you to find the justification in doing a mid-construction blower door test, because final ACHs are a lagging indicator of the root causes of the issues. And I know Ben also reached out to me to acquire his own blower door system, and that's what they did. So they've started doing mid-construction on their own blower door testing. They've noticed that some of when they isolate the areas that are causing problems in some houses and roll out solutions to that all across the board, they've noticed ACH reductions in the 0.25 to 1 air change per hour kind of range. They see air leakage as the most cost-effective way to improve the energy efficiency in the home. And then Ben also says, as an added benefit, has been how visual and educational mid-stage testing is. Trades can see firsthand how some small oversights during IPD stage can accumulate into meaningful ACH losses at final. It's been a strong driver of continuous improvement across the teams, helping everyone to understand where to focus their time and how to maintain the gains that we're achieving. So that's how someone like Mattamy Homes sees this. Slightly smaller home builder, custom lighthouse custom homes. We do their blower door testing. Right now, we're just doing them at mid construction. So they do pre-draw blower door tests as a quality control step. It allows us to catch air leakages while the home is still open and accessible. That makes repairs far easier and less costly than trying to deal with them after drywall and the interior finishing is complete. In Chris's opinion here, the air barrier is one of the best value when it comes to energy conservation. So testing it before the drywall just makes sense, helps improve the overall performance of the home, can reduce future warranty calls, and help prevent building envelope issues, including things like attic rain. Okay, we didn't talk on that, but that's something that we do a lot of testing on, diagnosing on, is if there's attic rain. Doug from Shane Homes writes, we conduct a few blower door testings on our units for a few reasons. To confirm the efficacy of the envelope and airtightness of our buildings, because air leakage has a negative consequences with respect to energy loss and homeowner comfort, as it creates cold spots in the interior spaces. So cold areas that are often inaccessible, such as behind furniture, with associated challenges like mold growth and the like. Shane Homes is also conscious of the transfer of air between units. So for their attached units there, with their party walls, in order to minimize this from occurring, even going as far as conduct smell tests to show that there's minimal to no air exchange between the units, resulting in transfer of cooking odor and other odors between neighboring occupants. Some of their advertising lately has leaned into this idea of a yell test or a smell test. You may have seen that in the Shane Homes regions. Blower door test shows minimal air movement. A smoke test uses a fog machine for this out more, and we were helping them out with that when we did the smoke testing. We filled one unit up with smoke, depressurized another unit, and then we could see where the air leakages were more effectively. And then third, being more proactive in construction practice for pending updates to the building and energy codes that have been more stringent standards for ACH and energy loss. He goes on to note that they've identified a foam gasket around electrical boxes, often being broken when the wires are inserted, and simply chasing that down, he's found a improvement of almost 0.4 air changes per hour on their attached units. So again, that speaks to the difficulty of ACH effectively reflecting air leakage through an attached unit, because it is a small leakage over a small volume. Even something silly as filling electrical holes through electrical boxes can have a significant impact on ACHs. Axel from Homes by Sorensen, we do his blower door test as well, his pre and posts. So the reason that he likes to do pre-drywall tests, it's truly the only time you can go through and do a thorough review of the building envelope. If there's drywall covering the poly, then you can't truly investigate your primary air and vapor barrier yourself. Upon review, it's extremely easy to rectify air leakage found without the drywall on, and it's easy to identify insulation deficiencies and rectify without drywall on. As a anecdote here, there's nobody who takes air tightness testing quite as seriously as the team at Homes by Sorensen does. They do a fantastic job. They're there with us. There's multiple of their team there when we're there doing this testing. They take it really seriously. He goes on to say, overall, without doing the pre-drywall blower door test, you run a large risk of your home will not perform at its final test. Even though the pre-board is not indicative of the final score, we have found that our homes usually tighten up by about 0.5 ACH once the board goes on. You can always add post drywall blower door test if you desire. Even then, the only way you can correct that is to take off the drywall. By removing drywall, you can, by taking drywall on and off, you can be more detrimental than fixing the leak you're searching for. So that's Axel's motive there. And finally, I have one more for you. Justin from Golden Homes. They build lots of things out in the the Chestermere area. As a builder, we strive to give customers the best possible product we can. After having some conversations with inspections and our team about some of the most important steps of the build, we realized the interior vapor barrier was our very high priority. Through this process, we have effectively improved all the other steel on our houses, limited warranty claims related to the interior vapor barrier, and are consistently being educated on how we can improve our systems. The blower door test have helped not only us as a builder, but also our contractors to improve their standard. I broke this part out here as a separate quote because he had some lovely things to say about us as a testing company, but I don't need to communicate that to you. That's not a sales call. He highly recommends these services to anyone who is looking to improve their product and reduce warranty claims. And Justin from the Golden Group, they've also done a fantastic job in improving their tightness over the 2.5, 3 years we've been working with them. Their mid-construction numbers are getting much, much lower. Their reports are very, very small for things that we find to complain about. So that is my presentation for you. That's my contact information. If you have any comments, if there's any questions, I'm happy to take them now, Frank.
Excellent. Thank you for that. I'd love to see all of those actual testimonies from builders doing this. So, yeah, any questions from the audience? Feel free to unmute and ask them. If not, I got one or two. You talked a little bit about air leaks between suites for like multifamily units. Do you want to talk a little bit more about kind of the importance? I think kind of Shane Holmes talked a little bit about the smell test and stuff like that, but why is it important to that we actually worry about our what is otherwise an internal air barrier between suites?
Yeah, so you're right. Shane Holmes did touch on that on theirs. Doug is over at the multifamily arm of Shane Holmes. So I've worked with Doug a lot on various projects over the last probably 3 to 4 years and trying to identify. So I guess the biggest issue with air tightness in terms of attached product is that the air tightness numbers that we have to report on EnerGuide labels does not effectively reflect the overall air tightness of that unit compared to it would a single attached house. By that, what I mean is at least 25%, quote unquote, 25% of that building is exposed to another building of approximately the same conditioned space, right? If we have an end unit, the unit is attached to is also going to be roughly 18, 19, 20 degrees throughout the year, just like the primary unit is. So it's not an energy loss issue as much as it is a comfort odor tracing kind of thing. So we've done testing on an attached house where the duplex owner on the left could smell what the duplex owner on the right had been cooking. So that's a comfort thing, so much as rather than an energy efficiency thing, right? There's a yell test. You don't want to be able to hear your neighbors. You still want to have that idea that it's your space. And air movement is a really good way of introducing noises and smells from other spaces that are not yours and that you have to deal with. It can decrease your satisfaction with the house. That's the biggest reason why it's awkward to do testing in attached products like that. Does that kind of get to where you were going?
Yep. Yeah. No. Yeah.
Okay.
Excellent answer. And yeah, air is sneaky. When air moves, it takes moisture with it. It takes smells with it. It takes sound with it really well.
Yeah, and when I'm doing my diagnostic testing, frequently we have to figure out how water got to where it got to. Just to emphasize your point there, water is dumb. Water flows down. But vapor is smart. Vapor will go wherever it wants, and then it turns into water, and then it becomes dumb, and then it turns into something that we need to deal with. So a lot of the diagnostic testing that we do is trying to define what stage of water goes where. But yes, you're right. Vapor is smart. It moves with the air. And that's a big problem sometimes. It's getting a lot better. The industry is getting a lot better at tracing that and figuring out how to stop it before it becomes a problem, but that is a definite problem.
Okay. Uh, Feel free to unmute if anyone else has a question. But are you seeing more tapes used for air tightness? Do you like tapes better than acoustical caulking? What are you kind of seeing, or what's your preference?
In terms of air tightness, I'm not seeing a lot of tape. I try and dissuade people from using tuck tape. On almost every site I walk where I'm walking with the insulator at a pre-drywall, I'm recommending tape here, there, or the other thing. And in that instance, I am recommending a specific airtight tape, like that bright green one I showed, the Sega tape, or Tescon's Vanna tape, anything that's rated airtight. I have been kicking and screaming enough that eventually some of my builders and some of my insulators do have a roll of this on site or in their truck to go between site to site. So I am seeing more of it. They are happy with how it's being used. That's kind of the biggest thing, right? I'm as long as the air gets stopped, I don't really care how it gets stopped. So if we can stop it with the poly and the acoustical sealant and compression, fantastic, great. You're planning on doing that anyways. If it comes to it where we need to put a tape on to stop that air movement, then that's the kind of the discussion we need to have. We need to have everybody on board for that. So usually we try and recommend it's cheaper, more cost effective, faster for everyone to use the poly and acoustical sealant. Um, but if there are situations where tape's required, that one where I showed where we had it was the all closed cell spray foam assembly in the steel stud house. I directed him. He after I visited that site, he went straight out to Performance House out in Edmonton and bought a box of Sika tape, right? Because we found all these little details that, based on how finishings go, there was no other way to get to the air barrier at this stage. So he had to go out and get a whole bunch of tape. So sometimes that's the conversation we have.
The question, how you mentioned it, but maybe go into a bit more detail. How do you integrate the thermal imaging camera or thermology with your air tightness, and what's the advantage of doing both at the same time?
Yeah. Okay. Let me see. I'll go to this one here. Um, so this one here, when I'm doing my thermography, um, on between May and October, it's a little hit and miss sometimes. Depends on the time of day, depends on the weather. So I'm trying to do both, right? So my process when I go and do a mid construction is I walk around the house first and I look at everything. I look at all floors. I start in the basement, work my way up, and then come back down and set up my fan if we're good to go. Then I do my air tightness testing for metrics. So if I'm doing a positive test to do the ACH, that's what I'm going to do next. And then I turn on the camera, and then I depressurize the house, and then I typically go to the lowest risk assembly, the lowest risk floor first. So if that's a conventional house with a batten poly attic space, I'm starting on the top floor because there's not a lot of leakage that I'm going to see with my thermal camera that I wouldn't be able to see visually, right? If poly's missing, if there's a sealant missing, I'm able to see that rather than having to look through the camera. Then as I come down the house, I'm looking at the assemblies that are harder to visually assess specifically. So in this one here, you can see this. When I come to this assembly, I can look and I can see, yes, this doesn't look right, right? But when I have the pressure on, what happens is I can physically put my hand at this assembly and I can feel the wind, right? This is at a stairway, so I could physically put my hand and feel the wind. There's another detail like this further on in the house where I'm standing on the basement slab and looking up, and I can see the cold air is coming in and around this assembly here, where the spray foam is non-continuous. So that's how I do both. That's how we go about and do this. Obviously, the thermal camera is most effective when we have a temperature difference between inside and outside. So right now we're entering the difficult time of year to do thermal imaging. Me and the team, we've got some processes in place to try and maximize the effectiveness of thermal imaging. But it is a really handy tool, and it's much more effective, I find, than filling the house with smoke and looking around on the outside. That doesn't really do a whole lot if you have to stand outside and then the wind's blowing and then you can't see anything. Or if you see smoke coming out of the soffit, that just tells you there's smoke coming out of the soffit. It doesn't tell you where the air is getting in from on the inside of the house, right? So in terms of tools, there's another tool is that's out there. There's a sonic camera that can visualize ultrasonic waves. And so that can also be associated with air leakage. We don't have one of those. There's an argument that it may be a tool in the future that we would use, but yeah, when it comes to air leakage detection, we're trying to use whatever tools are going to give us a fast and accurate method of identifying the air leakage and the severity of the air leakage so that we can communicate to the right parties whose problem it is and how to stop it.
Excellent. All right, we're almost or just about at the end of the hour, so maybe I'll sneak one more question in before we end it for today, and talk a bit more about the spray foam. So you've got a picture of the spray foam, and spray foam. So is it a vapor barrier? I guess when it's over 2 inches. What is your thoughts about using spray foam when it's not continuous, like as that picture shown, where you Yeah. What's your thoughts on spray foam?
You want this one or you want the one I was just on?
The one this one's fine.
Okay. Um, Spray foam's fine if if it's applied properly. Being in the diagnostics arm of construction, I've seen it go screwy. So some people will ask me when I'm doing diagnostics, would you put spray foam in your new house? No, I would not, if at all possible. Mainly that's coming from not that it doesn't perform well. I haven't seen enough data that the rigid applied spray foam remains where it's supposed to as the building shifts over the course of its life. I also haven't seen enough data, and the it's the most carbon intensive insulation we have. So those are the reasons why I would be against spray foam. When it's installed properly, it appears to work fine. It is resistant to airflow. It is a vapor barrier. There are some instances, like when you have eye joists in a rim, it's a really ugly place, or even open web joists in a rim. It's a really ugly place to do anything else. So it does have its place in general building construction. It is deceptive. There are times when you look at something and you're like, yeah, it looks great, and then you put on the air on it and you're like, oh, it doesn't look great. There's holes here, there, or the other, and those need to be addressed. So that's my short on spray foam.
All righty. Well, we are past 1 o'clock. So, any last questions from the audience? If not, thank you very much, Steve, for your excellent presentation on the mid-construction blower tower tests and why we should be doing more of them.
You're welcome.
All right, and hope to see you all next month.
Thanks, Greg.